In accordance with the customs of this university, I open the ceremony with a prayer. Spiritus Sancti Gratia, illuminet sensus et corda nostra. Please take your seats. Good afternoon, ladies and gentlemen. Following this ceremony via the live stream, my name is Roy Kessels. I'm a professor of neuropsychology at this university, and I will be the acting rector today. And I would like to welcome you all to this academic ceremony in which Mr. Vijayakumar will defend his dissertation entitled Principles of Parietal-Frontal Cortical Organization. And I would like to especially welcome those members of the promotion committee who are attending this ceremony via Zoom today, especially those from abroad and from Canada with a kind of a time difference. Thank you very much. So it's a special ceremony because we are only a small crowd present here at Radboud University, and the opponents and the candidate is joining via Zoom. And I now give the floor to the candidate of the degree of doctor.
With the permission of the Council of Deans, and in order to obtain the degree of doctor from Radboud University, Nijmegen, I would like to defend in public my doctoral thesis entitled Principles of Parietal-Frontal Cortical Organization. Dear family and friends, I have a confession to make. In the past, whenever you've asked me what I studied for my PhD, I've often answered starting with grand questions like, what makes us human? We would then proceed to have wonderful discussions about a bunch of seemingly unique human behavior. But I studied none of that. Well, not directly at least. So it's high time that I told you the truth. During my PhD, we studied brain regions that are at the back of your brain towards the top, called the parietal regions, and regions at the front of your brain, called the frontal regions. These regions are interesting because they're involved in a bunch of those seemingly unique human behavior. They're important for language, planning elaborate actions, learning, decision-making, and so much more. But in order to answer grand questions like what makes us human, it's not enough to study just the human brain. We need to compare them to that of other animals. We can do this at many different levels though, from the level of molecules all the way up to the level of brain regions. But even these regions don't work all by themselves. They're connected to each other in intricate, complicated ways, which can be grouped into their own families. That's the level at which we studied brain organization. You might have seen MRI scanners at hospitals that produce scans like this one. We use these scanners slightly differently to check where in the brain blood flow was increasing and decreasing at the same time. This told us what brain regions were talking to each other and hence in a way were connected. We use this information to get to the principles of organization, to understand the rules that describe how brains are organized. Because in this particular context, only in this context, interesting things happen when rules are broken. We do need to study many, many brains to be able to do this though. So in chapter 2 of my thesis, we came up with a framework to do just that. We applied data-driven methods to identify multiple overlapping principles of organization in the macaque brain. We showed that the connections in this macaque brain run in almost parallel streams between the parietal and the frontal regions, as shown here. We also showed that there is an onion layer-like organization in this network, where as you move away from the center, the farther away regions have preferentially stronger connections between each other. We also use these methods to describe how this network is organized in a hierarchical fashion. Having understood the parietal-frontal organization as a whole in the macaque brain, it was time to compare it with that of the humans in chapter 3. But instead of focusing on the whole of the parietal lobe, we chose to study just the lower half. If you saw a macaque brain and compared it to that of a human, well, this is about the size of a macaque brain. So you might imagine that it might have evolved by just expanding like a balloon in all directions. But we know that that's not the case. Some regions have expanded much more than others, and lower half of the parietal lobe is one of them. And instead of looking at just the connections themselves, we were looking for patterns in how these connections change within this region. And we found two modes of organization here. The first one was organized in this front to back organization where the patterns changed as you moved from the front of the lower half of the parietal lobe to the back. And the second one was organized in more of a center to outward organization. But interestingly, the organization in humans was similar to that of macaques, only in the half towards the front of the region, and the other half at the back was breaking rules of organization, which is pretty exciting. So far, we've been looking at principles of organization in the brain, but the brain does things. It gives rise to behavior, which we need to study in the context of evolution, because as a famous evolutionary biologist once said, nothing in biology makes sense except in the light of evolution. This brings us to chapter 4 of my thesis. But before we proceed, a bit of background. Right now, as you're watching this talk, only your screen is in the focus. And the surrounding room that you're sitting in is probably out of focus, right? You have this ability to move your eyes and direct your attention and focus at a particular spot because you have something called a fovea in your eye. The brain region that controls your eye movements is called the frontal eye fields. But here is the problem though. This version, a particular version of this region existed in early primates as well that could not focus their eyes on a specific spot because they didn't even have a fovea. But they survived in the wild by paying attention to different spaces in their environment without having to move their eyes. Now, this tells us that the brain region that's controlling your eye movements probably evolved to direct your attention in more than one modality. So if this is true, we should be able to test this by looking at how attention is directed in the brain while you're seeing and while you're listening. We decided to test this by asking healthy participants to come in for an MRI scanning session. And this is what they did. They were focusing on the fixation cross at the center of the screen, and we asked them to pay attention to one side, let's say, for example, to the right half of the screen, without taking their eyes off of the fixation cross or the plus sign at the center. A series of letters and numbers were then flashed in front of their eyes, and they were instructed to maintain focus when they saw 4s on the same side and shift their attention to the other side whenever they saw a number, for example, 2. Interestingly, they did this both while looking at the screens, and we also played letters and numbers in their left and right ear so that they could do this attention switching task while listening as well. We found that the same region, the frontal eye fields, was activated when our participants were shifting attention in both conditions, both when seeing and listening. This proves that this region mainly evolved for shifting attention rather than just moving your eyes. It was more active when they were shifting attention rather than when they were just paying attention. that, in a nutshell, is what I studied during the course of my PhD and what I will be defending here today. But if this presentation has gotten you a little bit more curious about the brain, I would consider this brief talk a success. So thank you for your attention. Having presented the summary of my doctoral thesis, I return the floor to the rector.
Thank you, Mr. Vijayakumar, for this excellent overview of your work. And before we move to the actual defense, I first want to introduce the people involved for those attending the live stream. Present via Zoom are the promoter, Professor Medendorp, and the co-promoter, Dr. Mars. And they are both from the Donners Institute at this university. And they will both remain silent for the most part of this ceremony, the defense part, because they were the candidate supervisors who already had many opportunities to debate with the candidate about his work over the last years. And the others who are attending via Zoom or sitting behind this table will engage in discussion with the candidate about his work, and I will introduce each of them later during the ceremony. And I would like to begin first by giving the floor to Professor Beckman. He was the chair of the manuscript committee. And this is the committee that already completed the written review of the manuscript and accepted it for this public defense. Professor Beckman is Professor of Statistical Imaging Neuroscience at the Donners Institute of this university, and the floor is yours.
Thank you. Esteemed candidate, let me first congratulate you on a wonderful thesis full of interesting gems and ideas, a nice overview of where the field is with regards to using data-driven techniques for estimating or characterizing what the organization in the brain looks like, and I'd also like to extend that to your supervisors. Excellent work. Now you start off, and that invites me to also start off right at the beginning with a description of some work by David Finessen and Matt Blesser about the fact categories. And in the light of these categories, I've been reading and focusing on chapters 2 and 3 in particular, and I was wondering what your views are on how things like functional heterogeneity and aspects of, for instance, spatial continuity fit into these categories. It seems to me that they are quite coarse, and I would like to hear your personal opinion as to whether the list of 4 categories, function, architecture, connectivity, and topography, really should be considered as 4 different categories on equal footing, or whether there's actually some systematic subcategorization to be done there.
Anita, thank you for your compliments about the work. About the question itself, I do believe that when studying large-scale brain organization, we could view these various organizing principles as more of an overarching rule under which the subdivisions and the heterogeneity are organized. So rather than viewing them as equal footing, I would personally view them as descriptions of brain organization at different levels. Mm-hmm. And each of them have particularly specific interest based on what aspect of brain function we might be studying. So, for example, looking into individual brain regions and studying its topography might be important. I'm sorry about the noise. Might be important when looking into individual regions' function and maybe dysfunction. Whereas overarching principles like, let's say, that of the tethering hypothesis or gradient-like organization might not inform us about the specific function of a subregion.
Okay, but let's get a bit more concrete. So their definition is that a cortical area is a distinctive region of cortex that differs reliably from neighboring areas. So it's kind of a recursive definition, right? They define an area by defining that area being different from neighboring areas. And then they have these 4 categories that are actually quite substantially different in how they relate to actual underlying biological objects and how these biological objects would structure once you actually look at it at different levels of a hierarchy. So the architecture, for instance, they talk about, gyral architecture, will break down very differently to how topography breaks down at different scales. I mean, it's great having an acronym, but I wonder whether that actually is a useful and accurate description of biological reality, and particularly when it comes to things like you mentioned later, that when we talk about function and connectivity, for instance, we can have spatially non-contiguous areas, but that won't be possible when it comes to topography and architecture. So how can you consolidate these two things?
Indeed, I entirely agree with you that having kind of like this recursive definition of defining a region by saying how different it is from its surrounding regions might be problematic. I would personally stick to talking about architecture of a region by definition of, let's say, how the organization of cell types change. That's like the most common one used. But the link between the structure based on the cell types that's present in the area and what it does as its function is still remains unknown.
Okay. Now, have I got time for one?
For brief question, maybe.
Okay. Then just pick your brains on how you think that maps onto functional multiplicity. In chapter 3, you actually show that there's multiple organizations that coexist. Is that not violating the fact principles and categories?
So it's basically a yes or no question, is that correct?
I want to say yes immediately, but the thing that I'm thinking about right now is essentially in chapter 3, when we find the overlapping principles of organization, we are reducing this multidimensional data into like nonlinear lower dimensional projection maps, right? So, and it's mainly looking at how connectivity changes across regions. And I think, given that we find multiple overlapping principles, it must be true. Like there should be changes in these connectivity patterns at the large-scale organization level, which does not agree with the main fact categories. So I would agree that it does violate.
Thank you. So
I think
we'll have to discuss this further.
I hope this answers your question. Thank you, Professor Beckman, for your question. And we move to the second opponent, Dr. Amier, and she is a senior researcher at the Université Lyon in France, and she was also a member of the manuscript committee. The floor is yours.
Good afternoon. So I first would like to congratulate you. I really enjoyed reading your thesis. I thought it was really clearly written, and I was really impressed by the methodology, the development of the methodology you developed. So I also really enjoy your talk. It clarifies a few points that were a bit unclear to me in the manuscript. So I'm going to ask you a first question about your first study. You say that in macaques, your results show that the connection between the parietal and frontal cortex follows both a core shell and a dorsoventral organization. So I totally agree with your results showing a dorsoventral organization. It also fits very well with the literature. However, for the core shell organization, I'm not fully convinced. I'm telling you why. I remember a track tracing study from Tane, Gariepi and Boussaoud in 2002, showing that, yes, the PMD has strong connection with the rostral intraparietal lobule, which you capture with your results, but that the main connection of PMD was the superior parietal lobule. They show that, yes, the PMD had a few connection with the more posterior IPL, but the main projection was to the SPL. So I wonder what you think about that and how you reconcile your results with that.
Honored Madam, thank you for the compliments, and I'm glad that the brief talk clarified some of the things. The tracer studies are the gold standard in our field. Now, let me try and see if I can think of reasons for why we might not find the exact connectivity results in our data. If we look at figure 2.6, in which we describe the affinity matrix and a summary result of what connectivity results we have found with this data, we notice that the dorsal premotor connection does connect with the superior parietal lobe. But interestingly, the dorsal premotor cortex includes the SMA on the medial surface, which has significantly high correlation in terms of connectivity with the medial side of the superior parietal lobe. Mm-hmm. I think because of the extent of the region, we might be finding results that probably don't coincide with the exact tracer data.
Okay, but isn't it against finally a core shell organization? Because finally your PMD is connected really to more posterior IPL. You know, if it was really a core shell organization, you might think of really the PMD connected to the anterior IPL and the PMD connected to the anterior SPL, right? But you still conclude that it's a core shell organization, right?
Indeed. The one figure prior to this where we show connectivity, maximum connectivity as we move from dorsal premotor to ventral premotor. I'm looking at figure 2.5a. Mm-hmm. We see that the peak of connectivity shown by the, in this case, yellow color, also moves from superior parietal to inferior parietal. That was one of the main reasons why we concluded that it does agree.
Okay, thank you. It clarifies it. I have another question about your last study, the fMRI study in human. So when I look at your maps and the maps involved in auditory attention and visual attention, and I don't see only the FEF. I see the FEF, I see the SCF that you don't talk about. And in auditory, I have the feeling that there is something, it expands more anterior. And I don't know if you know this very interesting literature from Lanzilotto about this new premotor area that he discovered in macaque, but it was 10 years ago. It's the premotor ear-eye field, the PEEF. That is, I wonder whether maybe you have something there. What do you think of it?
Indeed, we in fact referred to that paper as well while coming up with a hypothesis. I'm sorry if I made it sound in the thesis and in the talk that this was entirely our hypothesis and that it hasn't been shown yet or anything. There have been electrode activation studies in macaques that show that these previously what was being called as frontal eye fields have connections to the temporal lobe and elicit attention related changes in auditory modality as well. That's why they suggested frontal eye ear field as the name. Now, in our surface projection maps, what we wanted to capture mainly was the whole network of regions that are associated in switching visual attention and auditory attention. I must admit that this was more of an exploratory analysis. We could potentially conduct studies that involve some kind of individual variation in each participant's performance, and then look at involvement in their white matter connectivity data to determine how these networks are either lateralized or how are they involved differently in visual and auditory modality.
Yeah. Yes. The reason also why I'm talking about this PEEF region is because it has been demonstrated in the monkey, but not in human. So it would be really nice to have the homologue in human. And one can think that maybe the human doesn't have it because the human is not moving his ear toward the direction of the source of the auditory stimulus or the visual stimulus. But there is a very recent study in eLife who shows that even human subjects, when you ask them to do auditory attention tasks, their muscle here, if you record the EMG, it predicts where the auditory stimulus is. So that's why I think it's really relevant to what you did.
Well, thank you for your questions and thank you for the answer as well. So the next opponent is Professor Everling, who is Professor of Physiology and Pharmacology at Western University in London, Ontario, in Canada. He was also a member of the Manuscript Committee. Thank you again for being able to zoom in and take part in this defense.
Yeah, thank you very much. It's my pleasure to be here. Just a quick compliment for your thesis. I really enjoyed reading it. Really nice work. I'd like to start with some questions about project number or chapter number 3. I think it's really interesting, but it's also troubling, I find, a little bit, because you use 2 different macaque data sets and you got very different results, I think. Can you tell me why that is? Why do you think it looks so different?
Honored sir, thank you for the kind words. Our original motivation to use multiple data sets was to really study if these results agree across data sets, if these are generalizable results. But interestingly, as you said, and as we can see from the final figures in the chapter, the 2 data sets are slightly different.
They're quite different, actually, right? Which is interesting.
Fair enough.
Yeah.
When we started to understand where some of these differences might be coming from, we identified a few things. in Oxford dataset, just the overall strength of connectivity was less than in the Mount Sinai dataset. And in Oxford data, if I remember correctly, the dorsal prefrontal as well as dorsal premotor connectivity strengths, correlation values were much lower as compared to Mount Sinai dataset. And I think the overall connectivity with the lateral prefrontal cortex in Oxford data was also more varied in comparison with Mount Sinai dataset. I think there were islands of subregions that showed differences in connectivity in Oxford dataset.
Okay, so based on that, I would take from there that you would think that the Mount Sinai dataset is actually better than the Oxford dataset in this respect. Would you say that, or is it just different? So one question is, for example, to actually compare these data. Did you ever compute the temporal SNR?
Indeed, that's a great suggestion, and this is what we want to do next. I know that Mount Sinai dataset has also been extensively used in other studies, which have produced excellent results. One other difference in the way we treated this dataset from other papers is that we did not use ICA denoising techniques as well. So indeed, we would like to check if the data sets are fundamentally different or not.
Yeah.
Another potential...
I could just interrupt you, but the pre-processing steps were basically the same for the two data sets, or did you do anything differently there? Okay.
For these two data sets, they were exactly the same. Now, another potential difference might be just the group of these individual macaques have this connectivity.
I think that's really unlikely. I think that's unlikely. But for example, do these animals have implants? Do you know that? Or did they have implants? Cranial implants?
As far as I remember, Mount Sinai ones did, I think, because they were I'm sorry, I'd have to check again.
No, it's okay. I mean, the reason why I'm asking that is because if an animal has an implant, there's always the risk that, for example, one of the bone screws could just be a little bit too low and actually creates artifacts, right? I mean, we've had that in our own data too. So I think it's really important that you characterize the data. So temporal SNR for each animal, I think it's actually really important to see if there is a potential problem, right? I mean, if you have no signal in the area, it's difficult to get connectivity, right? So one question I then had, I mean, I think it's really good that you look at two different data sets, but again, you got two different results. So I think an obvious question would have been, why not look at a third data set, see what you find there. So maybe the Oxford data set is just an outliner, or maybe the Mount Sinai is an outliner. So, or you find something totally different in the third one, which then really, then it gets really troubling, right? I mean, that really questions the entire technique and the entire idea to compare between species, right? If the macaque data is so much more valuable than the human data. What do you think about that?
Indeed, absolutely. I suppose we did not go for the third data set mainly because of the time constraint of finishing the PhD, but this is something that we are currently working on. We are still working with this data set. This is not published yet because we want to absolutely make sure that we understand it to the best of our ability before we
that's a good point. Yeah, so I mean, I would strongly encourage you to get more data sets. I mean, they're all available now, and it probably doesn't even take that long for you to run your things, right? Let me just, I think I have another minute or 2 minutes, switch back to the previous questions that you got about the frontal eye fields. So do you actually think the frontal eye fields is just one area?
I have read various disagreements in where people have identified frontal eye fields. In fact, people have identified up to 3 frontal eye fields in humans that I know of. So it does get harder and harder to say just this one region is doing all of the work in the humans. So our mask that we used for PPI analysis, for example, certainly included all those regions. So
okay. Yeah, so I also think, also based on macaque work and also what we've done in marmosets now, I think it's different areas and they're not all involved just in control of eye movements, right? Other areas are really controlled in head movements and potentially even like in body movements. I mean, you're quoting Ferrier here, right in the beginning. I mean, Ferrier, so what did Ferrier find when he stimulated the frontal eye fields?
And may I ask you to be brief in your answer?
Okay, so you said saccadic eye movements, yeah, no, well, yes, but not just. He also found contralateral head movements and pupil dilations. So even at that time, it wasn't just eye movements. But so I'm going to finish there. Thank you.
Well, thank you very much for your questions. The next opponent is Professor Van Duffel, and Professor Van Duffel is at the Laboratory for Neural and Psychophysiology at the Leuven Brain Institute at the Catholic University in Leuven, Belgium. The floor is yours.
Thank you very much. Esteemed candidate, I really enjoyed reading your thesis. It's at the heart of what I'm doing myself and what I really love to do. So I really read it with a lot of interest. Of course, I have to challenge you, and I'm not going to challenge you. I'm not going to praise you for whatever I like really very much. And I would quickly want to come back to what Stefan just asked you. I was also very much disturbed by the differences that in the result from the 2 monkey data sets in that specific project. Because if I read your thesis correctly, at least the 2 first data chapters, the idea is to apply this to many more species, right? So if within one species you get that much variability that you are not able to explain easily, how can you do that then across many more species where data quality, and I think it probably boils down to what Stefan referred to, differences in TFNR and all kinds of issues that a particular data set may or may not have. How reliable will that if you expand it to many more species? And the second thing is that quite often you compare anesthetized monkey data, non-human primate data, with awake human data. So what is the additional complication of using anesthesia, which is the main, what is mainly available out there at this moment?
On it, sir. Indeed, the idea is to come up with generalized frameworks that could be applied in species that we don't understand really well, at least not just yet. Yeah. We started with macaque data precisely because we wanted to make sure that we get results that we can understand based on tracer data, for example. Extensive work over the decades on the macaque brain has provided plenty of information to study them at multiple levels of organization as well. I completely agree with both of you, and would have to concede that we are still in the process of understanding where these differences come from, and would not apply to other species until we understand exactly what is happening. That's going to be our approach, at least. About the anesthetized macaques, as far as I am aware, the anesthesia does not put them to sleep. It's enough to keep them immobilized in the scanner until the scanning session is done.
I not necessarily agree with that, because if it is just to keep them still, it would be even unethical, I think, in some of these experiments. But anyway, I honestly think that there are differences between anesthetized resting state data and result coming from it and awake ones for various reasons. But I would like to move also to the final data chapter, the FEF one, and the interpretation. And I think it's a very nice concept that comparing all the shifting of attention in the auditory domain and visual domain. But all the interpretation of your data is in the realm of selective spatial attention, right? May very well be true, but an equally valid explanation might be it's in both cases related to eye movements. We know that even if you do your very, very best to keep your eyes still and covertly attend to a particular visual stimulus, there will be, and there are plenty of studies out there showing that there will be very minor differences in eye position, microsaccades and things like that. I'm pretty sure that the eye movement cameras that you use are probably even not good enough to pick up all the fine little details. And you even write in your thesis that in the auditory test, the subjects had difficulties in avoiding making an eye movement towards the side that the attention was drawn to. So wouldn't be an equally valid interpretation of the result that this is just eye movement related data rather than attention related signals? And that would be the same, that would explain that you have exactly the same population of neurons active in both cases.
On its we stringently corrected for eye movements in this data set. And if I remember correctly, we scanned about 25 participants and had to discard about 7 or 8 of them because they did not meet the requirement for fixating within a couple of, within, I think, less than 0.8 millimeter of distance. But
well, how much is that in degrees? Because millimeter doesn't say anything. Because we have studies where we show like fractions of a degree, like 1/10 or even 0.05 fraction of a degree, systematic differences between the condition that the monkey had to attend left and right, and usually they are much better fixators than human subjects are.
Indeed, it might translate to 0.5 degrees in magnitude of
5 degrees. Well, that's a
0.5.
0.5. But even that might be another. You have cells in the FEF that are coding for very, very fine saccade amplitudes. Well, you have even fixation cells which might be induced as well in both cases. And I have actually another, if time permits, a smaller question. Even the rationale of using MVPA to make sure that you're talking or that you're comparing two different processes that they're using the same population or a different population of neurons. Do you think that holds true all the time, that this is sort of like a bulletproof method?
Again, I would like to ask you to be short in your answer. It's again a yes or no question.
Right now, I think yes.
And I think we have to leave it at that. Thank you very much for your questions. We now move to Professor De Bruijn, and Professor De Bruijn is Professor of Neurocognitive Clinical Psychology at Leiden University. And thank you for attending the ceremony and at least virtually returning to your alma mater. The floor is yours.
Thank you. Esteemed candidates, first of all, I would also like to congratulate you with your thesis. I really enjoyed reading it, and coming from a completely different background, I actually learned quite a lot, so thank you for that. I would also like to congratulate your supervisors with this impressive work carried out, as I now know, over the last 1,461 plus days. My question stems from my own background in neurocognitive clinical psychology, and the more I read your thesis, the more I started thinking about more practical applications of your research. I believe you have also given this some thought, as one of the aims of your thesis was to provide, and I quote, methods applied to other species in order to bridge the gap between them. Also in chapter 4, you suggest, for example, for future studies to focus on linking individual behavior to subject-specific association pathways, or to investigate frontal-parietal disconnections to compare deficits in redirecting attention. My first question is thus a very general one, and I would like to know if indeed you have given the applicability of your research more thought, and what would be, based on your thesis findings, be a logical first step, in your view, to apply your research or to extend it to new research domains?
Honored Madam, thank you for the kind words. With regards to the question, I personally feel more confident with the approach that we took in chapter 2, which is to first subdivide the brain into smaller regions. And we show in the thesis that we don't need to have exactly a certain number of regions in order to study connectional families. So having broken down whole of the brain into smaller regions, and then studying hierarchical nature of how these networks are organized and whether they show similar organizing principles like that of the dorsal ventral dissociation in pathways, or the core shell organization, or if they match with the tethering hypothesis. I think these would give us enough information to plan future studies to ask more specific questions. When it comes to chapter 3, where we try to use the Laplacian eigenmaps and gradient mapping method, since we found these differences in macaque dataset, at least I would personally be hesitant in applying this immediately to other species.
Okay, I'm sorry, but I'm just going to interrupt you a bit here, because I know we're a bit tight on time, because I was wondering if you would also consider applying your more general methodology or combination to psychiatric disorders. That would be, that's of course related to my own expertise. Because while I was reading, I also allowed myself to daydream a bit more about a future where a new research domain called comparative neuropsychiatry would finally be able to answer our long list of outstanding questions regarding the etiology of various psychiatric disorders. And I checked this on Google, so no one uses the term comparative neuropsychiatry, so that could either mean two things: it's a really bad idea, or it means I'm onto something. But I'll illustrate it a bit more. So, although other animal species can also suffer, of course, from depressive symptoms, anxiety, obsessive-compulsive behavior, more complex psychiatric disorders are still often regarded as quite uniquely human. And the most common example in this case is schizophrenia, which is also referred to as the price that Homo sapiens pays for language. Well, obviously, it's kind of presumptuous, I would say, to assume that hallucinations and psychotic episodes are only experienced by humans, but let's, for the sake of argument, assume this is true. We all know the images of anxious dogs or depressed birds, compulsively behaving zoo animals. Schizophrenia, however, seems to exclusively affect humans and perhaps non-human primates. Interestingly, eye-tracking dysfunction is one of the most widely replicated behavioral deficits in schizophrenia. And it's overrepresented in clinically unaffected first-degree relatives of patients, for example. Thus, the frontal eye fields, an area or areas, perhaps as I just learned now, of specific interest in your thesis as well, has also been repeatedly implicated in schizophrenia. And I was therefore struck by your discussion, both in chapters 4 and 5, of the role of the associate pathways, in particular the arcuate fasciculus, in switching auditory attention and its presumed role in language. So my follow-up question is just, do you believe that your thesis research could actually already represent a first stepping stone for establishing a comparative neuropsychiatry research field? And to what extent do you feel that your findings from chapter 4 could be helpful in understanding the etiology of schizophrenia? Or do you think this is way too far-fetched and I should just continue and stick to daydreaming?
Thinking on my feet here, I'm also tempted to daydream a bit now. We know that at least some of these dysfunctions are characterized as disconnection syndromes. So some kind of problem in white matter pathways would have led to miscommunication between regions, which would then manifest as some kind of behavioral deficit, or in some cases, potentially hallucinations. So I think we have enough ground to look into some of these organizing principles and see if there are specific enough deficits or changes in a subpopulation to characterize it as comparative neuropsychiatry. I think yes, we could head in that direction.
Okay.
Are you happy with this answer?
Yes, I'm very happy to hear that. Now we just need some money to do this. Thank you.
Thank you, Professor De Bruin, for your questions. And we move to the final opponent, Dr. Goossens, who is present here in the lecture hall. And Dr. Goossens is assistant professor at the Donner Center for Medical Neurosciences of this university.
Esteemed candidate, also congratulations from my part on your work. I find it fascinating results. But since I'm short on time and since I'm here to ask some critical questions, this is what I have to do. So one of the things that struck me is that you I'm a neurobiologist by training, and for me it matters whether a brain area receives input or sends input, and what the mixture of that is. And so if I then look at figure 2.6 of your thesis, I see bidirectional arrows there, and I was between those frontal and parietal areas, and I was wondering, is he now implying reciprocal connections between those areas, or is it actually the case that your data analysis, you use a data-driven method, which is elegant, I would say, but does it also simply not allow you to conclude whether there are reciprocal connections or? And is this not a problem in your attempt to compare species?
You're absolutely right in bringing this serious issue up. We used bidirectional connections to suggest that they're just connected. The arrows there are not necessarily meant to suggest direction of connection.
I'm happy with that. But let's take it one step further. You suggest connections, but is it also possible that at least part of the seemingly connected areas simply receive common input and therefore fluctuate in their activity?
Indeed, absolutely. Since we are heavily dependent on correlation of connectivity in these regions. There could be a third region that's entirely driving connections between what we see as connected regions.
Okay, so that's probably going to complicate the comparison between species, right? But nevertheless, you find these interesting structures in the activity patterns. And so, just to close off, I want you to speculate this hierarchical clustering of organization that you find. What does it mean to you? So, can you speculate what that might give? How does that hierarchy come about in terms of evolution? Is it related to evolution? Is it just not? Could you speculate on that?
Hierarchical clustering, in the way that we have presented the results, dissociates the strongest connections and the weakest, strongest correlations and the weakest correlations first. And usually, once they start subdividing into smaller branches, they follow a similar pattern. Now, let's take the two branches solution, for example, where we have one large area that has high correlation with our seed region and one that has either negative correlation or low correlation values. What we relied on when linking this to evolution was a paper by Senedies from early 60s that discussed how premotor cortex evolved from distinctly different root areas. So I think that the hierarchical clustering would suggest how or from what root areas would these have separated and evolved into different regions.
One other last, since there's a little bit more time apparently. So if you were to say it came up a little bit between the discussions about these two different monkey data sets, which looked distinctly different to some and not so distinctly different maybe in your eyes. Now, if you're going to compare species, how would you not just try and eyeball those differences, but would you also foresee some kind of quantitative analysis in this? How, and if so, what would be a nice way to go forward?
So we have been mostly working with group level data in both the first and the second study. I would probably study these organizing principles in individual brains and then find a way to characterize individual variation and use that as some form of statistical testing.
Ora est.
The defense is hereby concluded, and I give the floor once again to the candidate.
Having defended my doctoral thesis to the best of my ability, I would like to thank the rector, my supervisor, and co-supervisor.
I hereby adjourn this meeting, and the promotion committee will now retire for its deliberations. On behalf of the Council of Deans of Radboud University Nijmegen, we have decided to award you the degree of doctor. And I invite Professor Mededorp to discharge the task assigned to him.
In the name of the Lord, with the power entrusted by the law to the Council of Deans, I hereby confer upon you, Suhas Vijayakumar, born in Shimoga, the title of Doctor from Radboud University, Nijmegen, to which are attached all the associated legal and customary rights and duties with respect to academia and society. Congratulations, Suhas.
And I have the diploma here, I can show it to you, and we will make sure that you get it by express courier as soon as possible. The co-promoter, Dr. Mars, will now address you in the laudatio, and we may all be seated.
Most Honorable Dr. Vijayakumar, dear Suhas, you have just taken the degree of Doctor of Philosophy. Congratulations. This is a fantastic achievement, and both Peter and I are very, very happy with your results. You might feel that perhaps you defended your work not quite in the circumstances we all hoped for, but here we are together, at least in some form. And the journey that ends here today with you becoming a doctor started not, as you say in your acknowledgement, with an email telling you about the 1461 days to come, but it started, I think, with a conversation at the scanner. I had just returned to Nijmegen and I needed to operate the scanner a few times to recertify myself. So I asked my friend Egbert if he had an experiment running at the moment that I could help. And he said, oh, I've got this very nice MSc student, I'm sure he won't mind. So there I was, gate crashing your scan, and after we put the subject in as normal with an MRI scan, we basically had 45 minutes of time to kill. So, you know, I asked you what your plans were, and we got talking about what should you be looking for in a PhD. And I guess I sort of inadvertently promoted a particular way of supervision that you seem to like. So when I had a PhD position open, I can't remember if I approached you to apply or whether you spontaneously applied, but anyway, apply you did. And as usual with PhD job interviews, Peter and I had asked all candidates to prepare a short talk about their previous research. Strict instructions, 3 slides, maximum 5 minutes. So we got 4 presentations from other candidates, and then came Suhas. And basically he had a TED Talk-like presentation about his life up until now, how that perfectly formed him to be ideal for this particular PhD position. So after about 25 minutes into this talk, we decided we might need to interrupt him because after all, we still had an interview to do. But of course you got the job and thankfully you accepted. Now, as promised, a PhD has some ups and some downs, but I think mostly ups in your case. But there were some issues, of course, and I think focus was maybe one particular one. Suhas, you are, as we've all seen, you're interested in a great many things, and this is a fantastic quality. But sometimes it was a bit difficult to curb that enthusiasm. And I remember that, especially in the early days, every time we had an appointment, I promised myself to this time put my foot down. But then you would enter my office. Sorry, I'm a little bit late. My friends and I have been up all night developing an algorithm to read the scientific literature for us. Okay, well, at least you were doing science. But next time, sorry, I'm a bit late. My friends and I have been negotiating with a software house to sell our algorithm. Okay, but next time, sorry, I'm a bit late. I was practicing for zero gravity in the sky above Bordeaux. This really happened. But I think part of that was also due to some confidence. We were stuck with a particular problem in your first project for quite a long time, and I think it had some effect. And I think we turned a corner really during one of your visits to Oxford, when we were sitting in the kitchen with my 3-month-old daughter cooing in the corner, and we had spread out printouts of your results all over the table, and then we sort of talked and built in our head a picture of parietal-frontal cortex. And I think then it clicked. And of course, writing is something you're very good at, so writing the paper was no problem. And a very helpful reviewer then thought, oh, if this guy really understands it, then he could do it on the other hemisphere. So then all on your own, you basically had to do your study again, and you were able to do that very well, very quickly, and I think that really turned the corner, and the next projects you were on fire and unstoppable and completed them in very little time. Now, Suhas, it really was a joy to have you in the lab. Your enthusiasm for anything intellectually challenging is fantastic. And if you steer it in a particular direction, I think great things can happen. You should be really, really very, very proud of your achievements. We thank you, both Peter and I, for the trust that you put in us, and we look back on our collaboration with very much pleasure. You're now in a new lab, combining two of your great interests, your old interest in how humans learn, and your new interest in comparing brains. And I can guarantee you, whatever direction your many interests take you, as long as you keep your eye on the ball, I think you will do great things, and most importantly, you'll have a lot of fun and enjoyment along the way. So congratulations to you, and also to your loved ones, your family and friends who are all watching this online. I wish you a very, very wonderful day. I have spoken.
Thank you, Dr. Maas, for these kind words. On behalf of the Council of Deans, many congratulations with your dissertation and your new title, Dr. Vijayakumar, and your successful defense here today. And the university also would like to congratulate your loved ones who are joining this ceremony, have joined this ceremony via live stream. And we as university value our PhD laureates very much, and you can be very proud today as well. I'm also very interested in your algorithm for reading the scientific literature, may be very helpful for me. And I'm also glad to hear that your thesis and this defense may be the start of an entirely new research field, comparative neuropsychiatry. So thank you all. We have now come to the conclusion of this ceremony, and I would like to ask you all here present to stand. Because we end the ceremony with a prayer. Gratias tibi agimus omnipotens Deus pro omnibus beneficiis tuis, qui vivis et regnas per omnia saecula saeculorum. The meeting is now closed.